subcommittee of AGU Precipitation Technical Committee, and our main goal is to provide useful information to students and early career scientists in the precipitation field by informing them precipitation-related conferences or workshops and related papers, and we try to help create connections between students and early career scientists in the field. And this seminar is part of our main efforts. We have quarterly seminar series every year, and today's seminar is the second one of the year. And it's just like the first seminar, it will be given by award winners from the AGU 2023 Precipitation Student Awards. And the third seminar will be held in September, and it will be given by several experts in various research topics. And the last seminar will be held during AGU. Hopefully this year we will have town hall. We are submitted an abstract and we're waiting for the results. So, and the last seminar will be about sharing work experiences from the scientists in the different career stages. We have a lot of good reviews from this seminar, so stay tuned for the upcoming seminars as well. And if you want to hear more from us, please join our mailing list or follow us on social media. Today, Jan and Yashraj will be the two moderators of the seminar. So take it away, Yashraj and Jan.
Hello, good morning, everyone. Welcome to the ECSPrecip Seminar Series. This is number 2 of 2024. And today we have two speakers who are the winners of the Student Precipitation Award from last year's AGU. Now I will hand it over to Yashraj to give a brief introduction of our two speakers.
Thank you very much. Hello, everyone. I'm Yashraj. Thank you for this opportunity. I'm delighted to welcome and introduce our first speaker for the day and winner of AGU Precipitation Student Award, Omid Zandi, who is currently in his second year as a PhD student at the University of Arizona. His research journey began during his master's program at the University of Tehran, where he developed spatial precipitation data for Iran's orographically complex region. Omid employed a combination of gauge data, precipitation products, and environmental factors, utilizing spatial non-stationary methods and ensemble machine learning algorithms. Currently, at the University of Arizona, Omid is building on this foundation. He is integrating spacebound microwave and infrared observations of cloud microphysical properties and brightness temperature with meteorological variables using machine learning and deep learning models. This is to create long-term precipitation retrievals with a focus on high latitudes. Furthermore, Omid is keen about adapting these advanced techniques for real-time precipitation forecasting, ensuring timely availability of the precipitation data. Today, along these lines, he'll be talking on development of novel long-term ML-based precipitation product from AVHRR in high latitudes using various observational dataset and auxiliary variables from reanalysis. I welcome again Omid. The floor is yours.
Hey, thank you, everyone. Thanks for having me. I'm really glad to present my work here for you today. So let's get to the presentation. Okay, as Yashraj said, I'm going to present my work on developing a novel long-term machine learning-based precipitation product using AVHRR sensor in high latitudes using various observational dataset and auxiliary variables from reanalysis models. To just give you a brief introduction, as you know, infrared-based sensors present least direct information about precipitation. In fact, they just provide you with the cloud top temperature and they cannot penetrate into the clouds. But the good thing about them is that they provide high spatial and temporal resolution, long-term records, and they have global coverage, pole to pole. In this study, we want to take advantage of the AVHRR infrared observations to estimate precipitation at the daily time scale with 0.1 degree resolution with a focus on high latitudes. And by high latitudes, we mean 45-degree poleward. And since AVHRR goes back to early 80s, the retrieval algorithm allows us to develop a long-term data set, precipitation data set, which is necessary for climate studies. And also another goal of the project is to replace AIRS and TOPS infrared-based precipitation retrievals, which has been already been using in GPCP for high latitudes with a more accurate and higher spatial temporal resolution product. Okay, when it comes to machine learning, the first and most important thing is the input data set or the features, and also the label or the reference precipitation data that we fit to the model. The input data set that we use are AVHRR sensor observations on board 5 satellites, from which we use brightness temperature at 11 and 12 micrometer plus cloud probability. And also we have MERA2 reanalysis dataset, which from which we use wet bulb and 2 meters air temperature plus total precipitable water. And we have auto snow land classes, which gives us 4 land classes, including open water, snow-free land, snow-covered land, and sea ice. And for the reference data set or for the label, we try to use the most accurate available data sets in each zone. Better say, for example, from 45-degree to 70-degree, we use GMI observations, which onboards a GPM satellite. And from 70-degree to 82-degree, we use cloud-side snowfall values or estimations, and the rest is covered by ERA5 and ERA5 land. And after, because as you see, some of the products are level 2 products like cloud-side and GMI and AVHRR. After grading all these data sets, and collecting the spatially collocated pixels, then we just choose those pixels that satisfy a 30-minute time difference threshold. And then we come up with a huge data set for the training. As like any other machine learning models, we split the data set into train and test data set. We use 60% for the training and the remaining 40% for testing. And also we use a, let's call it double machine learning model or a double random forest, in which we have 2 models. One is a classification model that detects the precipitation, and the other one is a regression model that estimates the precipitation intensity. So the classification model classifies each sample into dry and wet event. If it was detected as wet, then we call the regression model to get the final estimated precipitation. And also for the validation part, we have 2 validation phase. One is based on the test data set, and also we generate daily precipitation maps for one independent year, which is 2010, and we compared those maps with iMerge version 7 and ERA5. Okay, let's head over to the result section. So the first phase of the validation is over the test data set. Here you can see the simulated intensity versus the reference intensity over the test data set. And we are using a logarithmic scale to for the sake of better visualization. And also we have 3 statistical metrics, which is reported on top of the figure. Based on the statistical metrics and let's say KGE, we can see a satisfactory accuracy of the trained model based on the test data set, but we have the issue of overestimating the low or light precipitation events and underestimating the extreme events. In fact, it seems like let's say we are drizzling everywhere and we cannot capture the high precipitation values. And as I told you, the second phase of the comparison is generating daily precipitation maps. Okay, let's look at this daily precipitation map, which is for 6th of January for 2010 for the Northern Hemisphere, 45-degree pole bar. And we have iMerge, ERA5, ERS, and the simulated product, which is the developed product. As we can see, overall, the large precipitation events or major precipitation events are captured in all of the products. But for example, AIRS seems to capture higher precipitation cores or covers more area. But in our case, we also capture the major events, but we cannot get the extremes as it was expected from the scatter plot. And also, if we just, for example, compare AIRS and ERA5, for example, over East Asia, over this part, we have some precipitation, 2 precipitation events which are not represented in iMerge and the sim one. Here you can see the precipitation maps for the same day, but over the Southern Hemisphere. And again, we can see that the major precipitation events are captured, but it seems like AIRS is generating also some moderate events which are not captured or presented in ERA5 and iMerge. And also, if, for example, considering if you compare SIM and AIRS with ERA5 and iMerge, you can see that over, let's say, Southeastern Australia, over this part, there are 2 precipitation events that are not captured in ERA5 and iMerge, which can be attributed to the fact that AIRS and SIM are infrared-based sensors, and they might see something. Sometimes they might see some different events in comparison to ERA5 and iMerge. Here we have the mean daily precipitation map for 2010 over the Northern Hemisphere. And again, you can see here that over the Atlantic Ocean, North Atlantic Ocean, we are somehow underestimating precipitation with respect to ERA5 and iMerge, and AIRS is overestimating. And the same behavior is also observed over the western of North America over Pacific Ocean. And if we focus on the Western Europe, you can see that, for example, AIRS is seeing less precipitation than ERA5, iMerge, and also the simulated product. Here you can see again the same mean daily precipitation map, but for 2010. But over the Southern Hemisphere. And as you can see, AIRS seems to overestimating precipitation in comparison to the other product. Here also you can see the daily quantitative statistics with respect to iMerge and ERA5 over 2010. So we want to report the overall statistics, overall accuracy based on just 4 metrics. We divide the statistics separately over Northern Hemisphere and Southern Hemisphere. And as you can see, over the Northern Hemisphere, AIRS and the simulated product shows the same agreement with iMerge and ERA5 in terms of almost all of the statistics. But considering only correlation coefficient, we can see that the simulated product is showing higher correlation coefficients in comparison to AIRS. And also looking at the southern hemisphere, we see that the simulated product agrees better with iMerge and ERA5 considering all of the statistics like KGE and RMSE and other statistics. And here you can see the mean zonal precipitation for 2010, again separately for northern and southern hemisphere for the 4 available products. Over the northern hemisphere, we can see that the products agrees well with each other. They show the same trend, while iMerge is seeing somehow less precipitation, but they all seem to show the same pattern. But when it comes to the southern hemisphere, it seems like there is a high discrepancy between the products where, for example, AIRS is showing somehow strange behavior where the precipitation increases until -55 degree and then it gets closer to the other products from -65 degree. And also the simulated one, the green one is aligned with iMerge until around -60 degree, and then it gets closer to the ERA5 from around -65 or 70 degree, which is somehow expected because we trained the model based on GMI, which is already used in iMerge from 45 degree until 70 degree, and then we shift to a combination of CloudSat and ERA5 from 70 degree. But also we show this somehow a strange behavior over -65 degree, where further analysis showed that the same behavior is also observed in GMI. But since here we are talking about 2010, we don't have GMI data, but we did the analysis for 2016. And it seems like GMI also has this jump over -65. And to just wrap it up and talking about future research avenues as well, we can say that the outcome of this study shows that the proposed methodology can provide precipitation data with comparable accuracy with ERA5 and iMerge version 7. And the results also indicated that the machine learning model can detect and estimate precipitation with comparable or better statistical scores, especially in the southern hemisphere than AIRS. And we only did all this analysis based on a few features, from which the most important ones are brightness temperature at 12 and 11 micrometer bands with total precipitable water from MERA2. And since we have AVHRR sensor on multiple satellites, so we can have several precipitation maps for each day, which helps us to aim for sub-daily temporal resolutions as well. Also, for future research avenues, currently I'm working on training everything based on coarser resolution, which might give us better or more significant relationship between the features and the reference data. And that was it. Thanks for listening. And I'm here to answer any questions.
Great. Thank you, Omid. Thank you for the talk. Thank you for keeping the time as well. Everyone, hang on to your questions. We'll get to it after the second speaker's presentation. Our next speaker and AGU Precipitation Student Award is Xinyue Liu. Pardon me for the pronunciation. She is in her final year as a PhD candidate at the National University of Singapore. Her research centers on hydroclimatic issues, particularly the hazard risk linked to the real-life impacts. Early in her PhD journey, and this is intriguing, she researched on the climate factors driving the locust plagues in Middle East, and North African region. To tackle this, she developed a data-driven framework to extract spatio-temporal features, quantify locust-climate relationships, and assess the compound risk of locust invasion. This significant work was published in Science Advances and was featured by NYT, Associated Press, and ABC News. Currently, Xinyue is investigating the spatial compound climate extremes, such as simultaneous extreme precipitation events in different regions, which can cause more severe impacts than some of such individual ones. She has created a knowledge-informed deep generative model to account for the spatial dependence structure of this compound climate extremes, and on which she'll be delivering the talk as well today. I welcome again Xinyue, and over to you.
Hi, thank you for your introduction. So good morning, afternoon, and evening, everyone. I'm Xinyue from National University of Singapore. So today I'm going to present the knowledge-informed deep generative framework for risk assessment of spatially compound extremes. This is just a deep generative framework, and it could be used to any type of the climate extremes, like precipitation, temperature, wind speed, but currently I only apply to the temperature data sets. So I'll first give you a brief introduction and then introduce my motivation and research question. Last year, the July has been recognized as the world's hottest month on record, and the widespread heat waves caused wildfires in North America and Europe. Many regions also have the temperature exceeding 50 Celsius degree. This can cause many severe consequences, such as drought, electricity shortages, crop uncertainty, and heat-related deaths. These kind of spatially concurrent extreme events are called spatially compound extremes. They can strain the shared resources and causing more severe consequences than the sum of each individual events. For example, in 1983, the global spatially concurrent events caused the global crop failure. Why do we need a knowledge-informed generative model for such spatially compound extremes? This is because this kind of events, it occupies only a small corner in the multidimensional probability space, which is composed of spatial climate variables. So theoretically, to robust access this kind of probability, we need more sample size. But practically, because of the low occurrence frequency, there is a lack of observational records. Traditional methods use like stochastic weather generator, climate models, and ensemble reinitialization to solve the problem. However, each of the methods has some drawbacks. For example, the stochastic weather generator, it can generate the trajectories for climate variable realizations, but it maintains only the most essential statistical properties, and it cannot consider the spatial dependent structure. And for the climate models, they suffer from high computational burden and also model bias. Recent years, there's another method called ensemble reinitialization. This kind of method, it perturbs several days before the extreme events, the historically recorded extreme events, and trying to see if there are any trajectories that can cause more extreme events. This kind of method, it is affordable computationally, but it constrains to selected extremes. Now, with the development of artificial intelligence, we have new opportunity to solve this kind of problem. For example, using the generative adversary network, which does not rely on the estimates of the likelihood. We can approximate complicated high-dimensional probability distributions and produce visually indistinguishable samples from the real data. However, for the normal GAN, it only emphasizes the average property. To consider the extremal behaviors, we need to explicitly incorporate the domain knowledge to the model. So my first research question is how to develop a generative model that considers the spatially extremes by incorporating the domain knowledge. And the second research question is, after develop such model, how can it improve the risk assessment? So I developed a model called X-bait GAN. For X, it means that the model considers the extremal dependent structure, and spate, it considers the spatial temporal coupling patterns. Basically, we have such X-bait matrix incorporated into the architecture as an embedding matrix. It will be introduced in detail in the next slide. Here, I just very briefly introduce the modules in the GAN. So it has the generator, which transforms the latent vector. Usually, it is a Gaussian noise, and it transforms the latent vector into some fake data. And for the second module, the discriminator, it will try to distinguish between the real data and the fake data. And the losses it generated will be fed back to the generator and discriminator separately, so that the generator learns to optimize to the real data distribution. The X-bait matrix is designed majorly considering the extremal correlation. So it is, you can understand it as the probability of two locations being concurrently extreme. And for the definition of this X-bait matrix, it considers the spatial temporal autocorrelation patterns. If you know the Morris I statistic, you will see that it considers the spatial autocorrelation and classifies the spatial pattern into dispersed, random, and clustered. So here, my matrix X-bait, it not only considers the spatial pattern, but also the temporal pattern. For example, for this specific point, it considers the current spatial map as well as the current time steps. And I consider one coefficient into my X-bait matrix so that it will emphasize on the extremal behaviors. When the two locations are concurrently extreme, then my model will emphasize on the behaviors to optimize. It will optimize to learn such extremal correlation. So such matrix, it is concatenated with either the real data or the generated data into the discriminator. So during the training process, the generator not only learns to produce the generated data similar to the real data, but also the X-bait matrix similar to the real X-bait matrix. My study area is the broad Middle East and North African region, which contains the 10 most vulnerable countries in the world, and they are most easily affected by heat waves. And my dataset is the NSAP dataset for my evaluations shown here. And the time period is for 1979 to 2022. The daily maximum air temperature at 2-meter altitude is a heat indicator endorsed by the World Meteorology Organization. And also the time duration is for June, July, and August, the boreal summer season. And my sample is nearly monthly scale. So here is the animation for a quick visual inspection. You can see that in the NCEP reanalysis data, there are some wave patterns from the west to the east and from the east to the west in the lower latitude. And for the X-bit synthetic data, it kind of reproduces such wave patterns. But for the baseline model, SpaceGAN, it is blurred and it does not reproduce such waving patterns. And for some quantitative analysis, such as the statistical properties, I first examined the marginal distributions at different locations. You can see that for the median values, both the X-bit GAN and SpaceGAN, they correctly captures the medians. But for the interquantile range, the X-bit GAN got more correctly than the SpaceGAN. It kind of underestimates the interquantile range for the marginal distribution. And if you see the temporal mean, the two models, they have visually indistinguishable temporal mean as the real data set. But for standard deviation, some high variability are missed in the baseline. I also have some matrix that is commonly used in the machine learning community, such as the Wasserstein distance. Here, I use the multi-scale Wasserstein distance to consider different levels of the spatial scales. And I visualize it by the multi-dimensional scaling so that it is easy to see in a two-dimensional plan. And you can see that the X-bit GAN generated point overlaps very well with the real data, while the SpaceGAN GAN, it has some missing point for the outliers. And for the two behaviors, I have such two metrics. For extremal correlation, although the SpaceGAN, it largely overestimates the extremal correlation. But my model managed to correct such overestimation by getting more points around the y equals to x line. The MSE is decreased or improved by 48%. And this spectral distribution, it characterizes the spatial tail dependence. So for the real data set and the synthetic data set, you can see the X-bit GAN, it is more similar to the real one, while SpaceGAN, it unrealistically overestimates such tail dependence. And the final part is on the risk assessment or some physical interpretation. So we can use the generative model on some fixed locations for bivariant spatial extremes. For example, the annual maximum for Pakistan and Afghanistan, those two country peers, and Pakistan and Sudan. I plot the bivariant scatter plot and CDF plot. For this one, the Pakistan and Afghanistan, the scatter plot and CDF, they are very similar to the real ones. But for the Pakistan and Sudan, the X-bit GAN is more similar to the real one than the SpaceGAN. This point is confirmed by the Candle-Stock correlation coefficient. So if you compare the two country pairs, and then you'll find in the first country pairs, both the models, they have very similar values to the real one. But for the second country pairs, the space gap, it overestimates severely for the real candle-stock relation. And besides, from the geographical location, the Pakistan and Afghanistan, they are neighboring countries. But for Pakistan and Sudan, they are one in Middle East and one in Africa. They are non-neighboring and far from each other. So this shows that XBitGAN is more capable of capturing the bivariant spatial extremes for both neighboring and non-neighboring countries. And based on the bivariant distribution, I also compute the return period. So this is the amplification factors for the two country pairs. I want to know, so for the intensity of extreme events in the real dataset, what are the estimated return period in the synthetic dataset? It is the return period of the synthetic dataset over the return period for the real dataset. You can see that in my model, most of the points, they are very near to the one value, but for the baseline model, it deviates from the one. And some, for this country pairs, it can be as large as more than 50 return period. So it means that the SpaceGAN, it will estimate a larger return period for the historical events, which means that it will have a lower occurrence probability estimated and underestimate the risk of rare events. So above are the bivariant extremes. This figure is for the multiple locations concurrently facing some very severe extreme events. And here, the x-axis is the number of cumulative exceedance, and the y-axis is the probability. And the threshold is 1 in 100 year event. I plot the real dataset and the two models, and also the spatial random case. For this one, I assume that each location independently decide if they are going to have the extremes or not. And the probability is just this threshold, so 0.09, 0.01. And then it will be a binomial distribution for all the locations. And the heat waves are spatially correlated. So we found that if we assume the spatial random case, then the risk will be underestimated. And the x-bit, it is more similar to the real case. Also, we found that x-bit GAN, it can extrapolate to some very rare spatial extremes. For example, for the extremes events that has like 200 pixels, it is not recorded in the historical dataset, but it is actually likely to have. So this is just my quick summary. And I want to introduce the spatially compound extremes that can amplify the impacts of the social-economic factors, but it is hard to model because of curves of dimensionality and small sample size. And using my model, it considers extremal dependent structure, and the spatial temporal coupling will correct the spatial behaviors. And also for the experiment and application set, we found that my model it correctly captured the spatial dependent structure and assess the risk of rare events. So that's all for my today's presentation. Thank you for listening, and I welcome any questions or comments from you.
Thank you. Thank you very much. It was an interesting talk. I hand it over back to Jan, who will lead the session further and take up the Q&A. Thank you.
Yes, fantastic. Thank you both for your great presentations. I guess now we can move on to the Q&A part. So anybody, if you have questions or comments, feel free to raise your hands, put the questions in the chat box, or at this moment you can unmute yourself and directly talk to the speakers. And I saw there have been some questions in the chat box for Omid. And I think Omid have done a good job addressing them. So yeah, just go ahead and ask questions. Yes, Jackson.
Yeah, so I'm trying to question for Xinyue. I'm not sure if I don't 100% follow everything you explained, but I noticed that you're using NSEP as a sort of like the comparison baseline and the training, like the driving model, if I understand it correctly. Can you easily apply it to another reanalysis product?
Yes, it can be transferred to either reanalysis or any climate model output. Actually, I have already applied to like CMIP6 data, but due to the time limitation, I did not show the results here.
And so do you need to, is it just like you take it and then you just paste it somewhere else and it works? Or do you need to do some training or adjustment of parameters?
No adjustment of parameters, but retraining, yes.
Retraining, okay. Got it.
Actually, I was thinking of this question. So one way to test or to do the transfer learning is train it on one data set. It could be one ensemble in the climate models or like the reanalysis and then transfer to the climate models. But I haven't do that test and I cannot say it is reliable to do that transfer learning directly.
Okay. Okay, interesting. Thanks.
Okay, thank you.
Yeah, Eugene.
I also have a question for Xinyue because I think Omid already answered all my questions. So maybe I missed this, but is this really like pure GAN, not conditional GAN? So you didn't use anything as condition?
No, currently it does not have any condition.
Okay.
So it cannot control the result for the generated samples.
Okay. Have you considered using some conditions in the beginning?
Yeah, actually, I have tried to add on the condition for like the first several time steps. Yeah, but the controlling performance was not quite good.
Oh,
I'm
really?
not so sure why it happens, but
oh, that's surprising.
Yeah, and then I was trying to using combine with the VAE model. So first, like the condition is first input to the encoder, and then I use the encoded information into my GAN model. Yeah, I was trying to use that type of framework instead of the pure conditional GAN.
Okay. And additional question to that. So one benefit of generative model is that you can create ensemble, right? Have you like tried that? And because I think I heard that one of the downside of ensemble, like generative based ensemble products are they have narrow distribution, narrow standard deviation among the ensembles. So I was just wondering, have you tried ensemble with your current model?
You mean did I try to generate ensembles for my model or?
Yes.
Yeah, actually, I have some results. So for example, in this one, the uncertainty for the either X-bit or spit then they are generated for the ensembles.
Oh, okay. Yeah, thanks. I think I missed that part.
Yeah, and also I think did I mention you mean did I mention the drawback for ensembles here or where? I'm not sure.
So I think if you produce ensemble from the generative models, then the distribution tends to be smaller. It doesn't represent the whole uncertainty is very skewed and
I think the uncertainty it depends. For example, if you are going to estimate the return period for the like 1 in 100 year or 1 in 1,000 year extreme events, then using the current data, because it's only 44 years historically, then you have to fit some GEV distribution, right, for the annual maximum. And then if you are going to bootstrap the uncertainty for the fitted GEV, then you will have very wide uncertainty for such fitted GEV distribution for the recorded data. But if we are going to use the ensemble samples, we can easily generate like 1,000 year event, and then the uncertainty will actually be narrow. But that thing is good because it decreases deep uncertainty.
I think my question was so the ensemble spread will be smaller if you create ensemble from the generative AI model. That's what I've heard. So I was wondering if you thought that as well.
Oh, in this thing, maybe I mentioned here for the range, interquantile range for marginal distribution. Is this what you mean?
Oh, is it running multiple ensemble from your models?
No, for this one, it's only the marginal distribution. So one point is one location, and the interquantile range and the median, they are for those different locations.
Okay.
Yeah, currently the interquantile range, it includes both the time steps and the samples, so it will have a range. But it is not the ensemble, because for ensemble we are trying to generate some uncertainty, right? But this one is just a marginal distribution.
Okay. Yeah, thanks.
Thank you.
We got a question from Lisa for Omid in the chat box. Did you check the jump at 65 south degree on CloudSat? I don't remember seeing it for snowfall only, but Lisa's wondering if you compared more than one product for this.
I haven't checked that because for that I have to collocate GMI with CloudSat so that we collocate and we collect the collocated samples over that latitude and then do some comparisons. So I think that's a good question or suggestion. I have to check that and see how much are they similar.
So you can also do just a clouds climatology thing and see the latitudinal trend. On the other side, if you want to collocate, there is a data set that is already ready for that. So if you want to check only that one, is CS-GPM. You can find it on PPS on the GPM website.
CS-GPM. Yeah, I have to take a look at that.
Yeah. Also, well, you compare AVHRR, right?
Mhm.
That didn't have the jump. Okay.
Yeah.
Thanks.
Yeah, you're welcome.
Yeah. Since this recording will be uploaded to YouTube, so there are a couple of questions that have been answered by Omid before, but I'm wondering maybe we can just repeat them so that people looking at the recordings will also won't miss this part. Omid, if do you mind if I like repeat the questions and you just maybe quickly overview them?
Yeah, of course.
Yeah. Yeah, sure. So from Jackson and Yongjing, I think a similar question of does like playing with different loss functions or adjust the weights or some strategies for the data augmentation would help to reduce the skewed distribution problem in your results.
Yeah, we have the problem of overestimating the light events and underestimating the extremes, and also that overestimation leads to a lot of tweezles and light events. So one way to solve that problem is like changing the loss function. But currently I'm using the default mean squared error loss function. And I have also tried different loss functions and other ways of dealing with this high skewness in the data, in the observation or in the summations. But I haven't been successful. I haven't been successful yet. Also, for example, if you give some weights to the samples, like the weight can be 1 over the precipitation value. So you are going to give more weights to the light events and less weight to the high events. You can get better result. You can solve the overestimation of the light events, but that at the expense of losing the extreme events. And that was not also helpful yet. And yeah, that's something that I've been dealing with as well.
Yeah, sure. And another question from Daniel, I guess it's kind of relevant to what Lisa just asked, is about the jump at 65 Celsius degree in 2010 is also apparent in GMI. Have you know the cause of the jump is and why other products are not capturing the same thing?
Yeah, I think when I visually compare the maps, I think the jump comes from it's a small place just at the tip of Antarctic near for example, the south of South America. And I think that place is like it might probably be sea ice, or it should be sea ice where it's where microwave products have some difficulty over that region. But again, that's something also that I have had on my mind. I should exactly look where does that overestimation comes from.
Yeah. Okay, thanks. And we have a new question in the chat box from Lisa. So for Omid, have you also tried to compare occurrences, or did you focus on snowfall rates only?
Currently for this task, I've been focusing on snowfall rates only. Yeah, because I need the I need intensities to train the model with.
All right, thank you. I think we still have time for maybe 1 or 2 quick questions.
So I have just a quick comment. I did a work at some point on Antarctica, and the Antarctic Peninsula is actually a very snowy place. I checked it with CloudSet. So if you want to compare something, there's a paper I wrote in 2018, and you have a visual. I compared ER5 and CloudSet at that point. So maybe that might help understanding something. But I also understand that gprof might, overestimate the occurrences. For example, if it sees, sea ice over there, there's Antarctic ice sheet over, that Gulf over there. So that might be another reason for that.
Yeah, and then when they incorporate GMI estimations into iMerge, I think they somehow post-process gprof observation or estimations over that area. That's why we don't see that in iMerge daily.
Okay, we might filter.
Yeah, they might filter that area out. Yeah.
Well, I have a quick question for Xinyue. So it's on your presentation, I think slide 16, and you are mentioned some matrix, I guess. Yeah, called Worcester distance.
Yes.
Yeah. Yeah, I'm just, maybe I have missed it, but could you provide more clarity, like what does it measure, and do you have a threshold for this matrix that above which it's good or not good?
Yeah, thank you for your question. So Worcester distance, it measures the divergence or dissimilarity between two samples. So if it is applied to just the original samples, then it will be this layer. But here I add on the sliced and multi-scale. For sliced, it is just a way to efficiently compute the Worcester distance. And for multi-scale, it can compute the different spatial scales. So for example, for the original sample, if you down sample, and then the resolution and the size will be much smaller, and you are considering from very fine spatial pattern to the coarse spatial pattern. So it compares the different levels of spatial patterns. And regarding the threshold, because it is comparison between two models for the baseline and my model. So it does not have a threshold as which is good and which is bad. But basically, the smaller the value is, it is better. And I'm showing the figure here because it is a high dimensional matrix, because I compare the Worcester distance between two samples, and the two samples can be either from the real dataset and real dataset, or generated and generated, or real and generated. So it is a high dimensional matrix with 4 blocks. And then I transform such high dimensional matrix to this 2-dimensional plan by some manifold learning method. And then it will be much easier to visualize it. You can just say if it is overlapped, then the distance is smaller. And if it has large deviation, then it is not similar to each other. So that's all.
Yeah, that helps. Thanks.
Thank you.
Okay, yeah. I think that brings us to the end of the seminar. And thanks again to Omid and Xinyue for your great presentations. And thank you for everyone for attending the seminar. And this is again the second seminar this year. So as Yongjing mentioned at the beginning, please stay tuned for future seminar events.
Thanks, everyone. Bye.
Bye.
Thanks.
Thank you.
Bye-bye.